Ramps. Okay, so ramp problems are a little more unique because we change our orientation system to parallel to the hill and perpendicular to the hill. So we're going to work through a couple examples. I want you to pause the video and jot these down, and we'll work them out together. Okay, so when you're looking at these problems and you visualize the motion, if there is any motion of the box, it's always going to be parallel to this hill. It's not going to like shoot off the hill or into the hill. So we're more concerned with this parallel component when we talk about the acceleration or the net force. It's typically going to line itself as parallel to the hill. So looking at this first problem, they have a 20 kilogram box that's sitting on a hill at a 30-degree angle. They give us the coefficient of static friction and the coefficient of kinetic friction. And they're just asking, is the box accelerating? So in order to know that, we'd have to know, based on its forces, does it have enough force down to overcome that static frictional force back up? If it has more force down the hill than up the hill, then it will be accelerating. If there is more force down the hill than up the hill, then this static coefficient isn't going to be enough to keep it supported, and it will in fact be sliding, and then we're going to be using this kinetic coefficient in order to solve and figure out what's going on. So let's zoom out. Right, so when thinking about the free body diagram for that box on the hill, if we visualize those forces, it has a force of gravity straight down. I can just call that the mg value. It has a normal force off the hill surface. That's the surface pushing 90 degrees to the ramp itself. And then it's got frictional force up the hill. And you see that these frictional forces and normal forces align themselves perpendicular to each other. The next thing we do when we have a ramp problem after we get done drawing our free body diagram is we break up that component of weight that doesn't align itself to the ramp, because friction is parallel to the ramp, normal force is perpendicular to the ramp. The weight vector is the only one that doesn't align itself to that plane. So I will always break up the force of gravity perpendicular first and then parallel. And the reason why I always do it that way is because this angle then will match the angle that was off the horizontal. And so if you're just consistent in that, where you always break perpendicular to the hill first, like go against the normal force first, and then go parallel to the hill, you should get that solved correctly. Be sure when you turn and go to the end of the weight arrow that you don't go all the way down here and then go straight across. The 90 degrees should be between your perpendicular vector and your parallel vector. Now, talking about those sides, this is the opposite side of the angle, this side down here, and so that is going to be the sine component, and this one would be the cosine component. If you have a hard time remembering, how do I know that that's sine and that's cosine? There's a little mnemonic that sine slides downhill. The sine slides. So the sine component will be the one that's sliding down the hill when you break that gravity vector up. And but the real math behind that, just kind of off to the side, is that if you have this right triangle and you have the hypotenuse here and you had this angle here, if you're interested in expressing the adjacent side, this would be the opposite side. The adjacent side would be a cosine function. You'd say the cosine of the angle equals the adjacent side over the hypotenuse. So solving for A, you'd multiply each side by hypotenuse. And that adjacent side then is equal to the hypotenuse times the cosine of the angle. Well, that's all I have here is the weight, that's the hypotenuse, times the cosine of the angle. If I want to talk about this opposite side, it'd be the same thing. I would just do it with the sine component. Sine of theta equals opposite over hypotenuse, multiplied by hypotenuse. And now that opposite side could be talked about as the hypotenuse, the diagonal line, multiplied by the sine of the angle. So that's all these are. Mg sine theta, mg cosine theta is just expressing those lengths in terms of this length. And it's helpful to do that to get to some of the other math that we use. So now we're going to figure out what it's actually doing down the ramp. I'll just kind of move that over here, zoom out a little bit. And the whole concept is that they gave us a static coefficient. And from that static coefficient, we can figure out what is the maximum frictional force that this thing can hang on with before it starts to slip. Remember, static friction can be any amount from 0 up until this maximum. So this is a maximum value when you use the coefficient like this. And our friction may not be pushing up that hard, but if the amount down exceeds this calculation, then the static friction isn't able to hold on and it'll break free and the sliding friction will take over. But if we solve for a value down the hill that's less than this maximum amount, then we're in fact not actually using all of that static friction. We would just only be using whatever is pushing down the hill. The static friction would be matching it up the hill and this thing will be at rest. So let's figure out what that max is to guide us for the rest of the problem, and then we can set up our net force equations. So if I have a static coefficient of 0.84, I would have to know what the normal force is, and the concept here is that the normal force should match the mg cosine theta. It is perpendicular to the hill, and the amount off the hill is matching the amount into the hill. So I had expressed that normal force as mg cosine theta. And when I solve that out, the weight is 200. The cosine of 30 is around 0.86. And multiply that with 0.84, you get around 145.5 newtons. So that's the maximum that this thing can hang on with. So, all right, let's figure out what's going down the hill. The amount down the hill is equal to mg sine theta. All right, and if I solve that out, that's just 200 times the sine of 30, or that would be 100 newtons. So I have 100 newtons going down the hill. I can withstand up to a maximum of 145 back up the hill. So the static coefficient's large enough that I'm withstanding this 100 newtons that's pulling down the hill. This object is in fact at rest because that force down the hill does not exceed the maximum amount of static frictional force that can push up the hill. So there's really no need to calculate acceleration. There's no need to use the sliding coefficient. In this case, this object, the static coefficient's large enough to prevent it from sliding down. If you wanted a real value, if they said, what is the value of frictional force on this problem? It's not 145, it's not the sliding friction, it's the fact that this is at rest. The concept there is that then this vector should be the same as this vector. So for this problem, that friction is less than its limit, and it would be at 100 newtons to match the 100 newtons that are going down the hill. Just for practice, let's go ahead and write out the net force equations. You don't need them much in this problem, but we'll still get in the habit of writing them each time. The net forces that are parallel to the hill would be mg sine theta down the hill minus the force of friction up the hill. And we're not going to phrase this as mu times normal force because honestly we're not talking about being at the limit. So we're not going to use this coefficient of static friction because we're not actually at the limit of that amount. So we'll just say it as minus frictional force, and that should equal 0. And then all that states when you rearrange that math is that the frictional force is equal to mg sine theta for this problem. If we go the perpendicular direction, then we have the normal force off the hill minus mg cosine theta, and that also equals 0. And this was how we were able to solve for the normal force to theoretically figure out what that limit of static friction is set it equal to the mg cosine theta, and that just shows up again in that perpendicular equation. All right, so that's one example. We're going to actually now do part 2, where there's some acceleration taking place. All right, in problem 2, you have this box of 5 kilograms that's accelerating down the hill at 4 meters per second squared. And anytime they give me a mass and I know the acceleration already, in my head, I'm just quickly saying, hey, they just gave me the net force. Net force is just mass times acceleration. So the net force on this object just is 20 newtons. It's something that I'm going to come back to and I'm going to put in my equations, but it's just a good habit. If you have mass and acceleration information, just scratch out or off to the side, write out what is the net force on this box, because that is going to come back into play when we get it set up. So let's start with our free body diagram. We have a downward force of gravity, and we have a force perpendicular to the hill. That would be our normal force. And we have a force of friction up the hill. And the whole concept here is if it's accelerating, then we know that the amount of force down the hill, this component of gravity down the hill, we know it's bigger than the frictional force up the hill, or else it wouldn't accelerate. So I just broke that gravity up. Notice it didn't look I didn't break it, over and down like I did on the last one. I'm not always picking the same side to break it. I'm always picking the same order to break it. So it's always perpendicular first and then parallel. So now that the ramp has changed orientation from the first problem, perpendicular is this way first and then parallel. And if you always get in the habit, that's what places that angle correctly for you, that's sandwiched up between the gravity and the perpendicular component. So again, I have mg cosine theta, and I have mg sine theta. And now we're ready for our net force equations, since we got everything broken up. The net force parallel to the hill would be the mg sine theta down the hill minus that force of friction up the hill. Well, I can actually phrase the force of friction in variables, but for just conceptually, I'm just going to write it as the force of friction, so we know what that is. And then I'll finish that phrase with that equals the mass times the acceleration down the hill. Now keep in mind, we already know what that value is. We solved that right at the beginning. That equals 20 newtons. But just on the next line down, I'm going to expand out what friction is, so we can see that equation. That's really mg sine theta minus mu of sliding friction times the normal force. Well, keep in mind the normal force is the same size as this mg cosine theta. So that all equals ma. So that is really the phrase that we're going to be using to get to mu. And I don't necessarily have to write my perpendicular equation to find that mu because I have everything else I need. I was given mass, I know g, I know the angle. Again, I know m, I know g, I know the angle, and I know mass and I know acceleration. So that's going to be everything I need. I'll just do the algebra here in a second. But to prove that that normal force is the same as the perpendicular component, I can write a net force perpendicular equation and say, all right, well, the normal force off the hill minus mg cosine theta into the hill is all equaling 0. And that is why normal force is the same size as mg cosine theta from this statement. So now it just becomes a matter of plug and chug. Algebraically, if I, let's say I add this to the other side, and then subtract ma from both sides. Kind of do a two steps in one here. Then I'll end up with mg sine theta minus ma equals mu sub k mg cosine theta. All right, well, I want to get rid of that mg cosine theta. We're just going to cross that out. So now I'm left with just mu k. But I got to divide that all the way over here too. Mg cosine theta. Now be careful about just like crossing things out. I don't want to get too carried away and say like, oh, there's an mg on top and an mg on the bottom, because there's not a g in this term. But there is a mass in every single term. This has a mass, this has a mass, and this has a mass. So you're safe with crossing out the mass. Let me just erase, kind of clean this up a little bit so I have some room here. So you can cross out the mass. That's okay if it's in every single term. And now, finishing that out, I'd have g times the sine of the angle, which I picked 30 to make that math a little bit easier. So that's 10 times the sine of 30, or 0.5, minus the acceleration in the problem, which was 4. And that was all divided by the cosine, g times the cosine, or 10 times the cosine of 30. So what that ends up equaling is 5 minus 4 is 1. And then 10 times the cosine of 30, that's like 8.6-ish. So final step then, divide those out. Coefficient is somewhere around 0.116. Remember, there's no units to a coefficient because it's a unitless ratio of friction to normal force. So that's as far as I can take that one and get the coefficient of sliding friction of those two surfaces.